Hello ladies and gentlemen, welcome to my lecture series Modern Gravitational Theory. This is a lecture besides the normal series. I want to present the Huppmann metric. It was derived by the German physicist H. Huppmann. His problem is he cannot practice his profession as a scientist in Germany. He is, like many other qualified people in Germany, forced leaving the country to immigrate. In Germany, obviously, there's only nepotism and protection. That means the top 10,000, the rich ones, do everything amongst each other, and all the others are the idiots. H. Huppmann comes out of a rather poor family, so he has no chance to do anything in Germany. Meanwhile, there's obviously exodus in Germany. Everybody is leaving the country, especially scientists. Congratulations, the other countries, you can get high qualified people from Germany. So we are asking ourselves, what is happening there in that country, in Germany? Okay, we don't want to discuss the politics of Germany, we want to discuss the Huppmann metric. H. Huppmann tried to publish his work in several journals, but no one wants to print it. There is obviously always some persons who peer review their works among each other, and if anybody else wants to publish something, then the works are refused. So we are asking ourselves, what is happening there in sciences? Obviously, scientists don't want to make any progress. H. Huppmann is obviously in the same situation like the Nobel Prize winner in medicine in 2023. They had also the problem to publish their work and couldn't do that for a very long time. Okay, if H. Huppmann cannot publish his works in a normal journal, then I will publish them here online. Perhaps it could be a big breakthrough in physics. Okay, and now I'm proud to present the Huppmann metric.
This is a paper. I think it's a version for the Physical Review. The title is Inner Static Spherically Symmetric Solution in the Relativistic Theory of Gravitation, RTG. This solution, together with the Fock solution for vacuum, represents a complete alternative spherical symmetric solution to the Schwarzschild metric in GTR, the general theory of relativity. I read the abstract. With the intention to develop a singularity-free geometry in gravitational theory, the inner solution for RTG is derived in analogy to the Schwarzschild metric in GTR, which is mathematically more complicated than in GTR. The mathematical singularities lie completely outside the range of definition for the radius variable. It is shown that only the assumption of a constant mass density makes it possible to derive an analytical solution. Realistic models with no constant density function must be calculated numerically. It is also shown that the Fock metric can be derived out of the inner solution as a limit case for the vacuum. The new RTG metric is compared to the Schwarzschild metric. It yields some interesting conditions, especially for very compact bodies like neutron stars or black holes. Certainly, a black hole is not a singularity. It must have a definite radius and density. Now the introduction. A spherically symmetric metric can be represented by a diagonal form of the metric tensor, the equation 1. So here we have the four diagonal elements for the metric tensor. We have three unknown functions, a, b, c, which depend on r. in the fourth component, there is the same like in the third one. There is only an additional factor, sine squared theta. In other papers, some other parameterizations are found, but it makes no difference which parameterization is used. The mathematical problems stay the same. So the easiest parameterization is used here. There is, of course, a variation principle by using a Lagrange density, which yields the field equations 2 that can be found in 2. At the end, I will show the complete literature list. The field equations are obviously the same like the Einstein-Riemannian field equations in GTR. Yes, that's true, but the background is another one. It would lead too far to explain that in detail now. By looking for an outer solution, vacuum, the energy momentum tensor would vanish. Here we are looking for an inner solution. That means space is filled by matter. The tensor T does not vanish. We suppose an incompressible fluid of a spherical shape in analogy to the derivation of the inner Schwarzschild solution. So the tensor T is diagonal as well. And in the covariant version, we find the functions a, b, c again here. And the two unknown functions for pressure, P, and density, rho. And now we come to a very important point. To simplify the differential equations in the Einsteinian theory, an arbitrary coordinate transformation is executed. It is possible to use an additional coordinate condition. The condition that is used in GTR has the aim to simplify the differential equations. H. Huppmann calls that Schwarzschild gauge. But the question is that gauge realized in nature, or does this gauge leads to equations which describe nature correctly? Obviously not, because it leads to singularities. Singularities are unphysical. They are an indication that the theory is wrong. Here, equation 4 is used as an additional coordinate condition. It describes gravitational fields with spin 2 and 0. It was obviously first used by W.A. Fock in the 1960s. So H. Huppmann calls it the Fock gauge. It would lead too far to explain in detail now why it is advantageous to use such a coordinate condition. In RTG, we suppose first a flat space. Later, when we put some fields into that flat space, we will get an effective Riemannian space. So the gammas with 3 indices here are the Christoffel symbols in the flat space. In 6, there is a Minkowski metric in spherical coordinates. If we carry out the standard procedure, that means we use metric 1 to calculate the Christoffel symbols, then the Ricci tensor and the curvature scalar, and substitute in the field equations, then we obtain equations 7, 8, 9. and 10 is the additional equation from the coordinate condition. Now, the system of differential equations must be solved. The field equations in gravitational theory are of second order and they are quadratic. That means not linear. So, there is no standard procedure to gain a solution. And whether an analytical solution exists at all is unknown. Huppmann had executed a gigantic algorithm of algebraic transformations. Here, the same simplification is made like in deriving the inner Schwarzschild metric. A constant mass density is supposed. I won't show the detailed derivation of the components of the metric. That would let Huppmann the possibility to publish the work still in a peer review, perhaps. The first step is to uncouple the system of differential equations. After some algebraic transformations, a linear differential equation of first order can be obtained, here 13. The equation is solvable for the function u if the coefficient functions f and g are known and integrable. Although the functions f and g are not explicitly given, it is possible to integrate the equation. To determine the integration constant, a continuous connection to the vacuum solution, Fock metric, is supposed. So the boundary conditions are these, 18. There is a parameter alpha in the Fock metric. It is the mass multiplied by the gravitational constant divided by c squared, c speed of light. So the integration constant can be determined, 19. This leads to equation 20. Here, the still unknown function b is only dependent on function c. So the differential equations are uncoupled. Now it is possible to substitute b by an expression with c. Then an equation can be obtained where we have only c with its derivatives. The problem is, the equation is very complicated and must be calculated numerically. Now we come to the determination of the G22 component. Huppmann was executing a gigantic algorithm of algebraic transformations, and then he could derive a simple differential equation with only c and its derivatives. Here, 24. Here we have the second derivative and the square of the first derivative divided by the function itself. This can be integrated easily. The solution is an exponential function. It's a differential equation of second order, so we have two integration constants in the solution. We use the ansatz 25 with the integration constants k1 and k2. We use again the boundary condition 18, the Fock solution, to determine the constants. And so the first component, G22, is determined, 26. There is a constant factor r, the radius of the body, plus the constant in the Fock metric, squared. In the exponent, we have a factor 2 and a fraction with the radius variable minus the radius in the numerator, and again the sum of radius and alpha in the denominator. So the first function of the metric, the G22 component, is determined. Here the abbreviations beta and F are used. Now we can determine the functions B and P, the pressure function, easily. B can be obtained immediately by substituting C in 20, the equation where B is only dependent on C. So B is determined 28. In a similar way, P can be obtained. It is no problem to obtain an equation with P but without A, and then everything can be substituted. So the pressure function is this, 29 here. Now, only the function A, the GOO component, is still unknown. Normally, it is no problem to determine the last unknown function if all other ones are already known. But here, the situation is completely different. It is indeed a problem to determine the function A. We consider two possibilities. There is a relatively easy possibility to calculate A analytically. We consider the covariant conservation law, here 30. If the energy-momentum tensor and the Christoffel symbols are substituted, we would obtain an equation with A and its first derivative. That can be integrated. The result is here 32. The integration constant can be obtained again by using the boundary values of the Fock metric. So A is now determined. Here 33. Another possibility to determine A makes it necessary to execute an integration numerically. We integrate equation 10, so 34 here is obtained. Or then, using an exponential function that yields 35 here. We use again 18 to determine the integration constant. And so 37 here is obtained and A is determined. The integral must be calculated numerically, but the functions under the integral are given analytically exactly. So it is possible to determine the integral very exactly. Now the metric is completely determined. Here I want to show the complete Huppmann metric. Now we want to analyze the Huppmann metric. It must be possible to obtain the vacuum solution, the Fock metric, by considering the transition to vacuum. That means ρ vanishes and the radius r goes over in the radius variable r. And indeed, we obtain the functions of the Fock metric, here 38. Now we come to a very important point, singularities. The appearance of singularities shows us whether a metric is usable or not. The G22 component cannot yield a singularity. It is completely uncritical. The G11 component could yield some singularities. We set the denominator equals 0, 39. because of giving H. Huppmann the chance to publish his work in a peer review, I don't show the complete, complicated mathematical calculation. A cubic equation must be solved. That means 3 singularities are possible. So we have equation 46. The 3 possible singularities must be examined now. Here in 47 we have the first value for r. Again, I don't show the whole calculation. The result is r1 is bigger than the radius r, 52. So the value lies outside the range of definition. We are talking about the inner space, which has the range from r equals 0 to the radius r. For the outer space we have to use the Fock metric, though the first singularity does not cause any problems. Good. R2 would not yield a real value but a complex one, so there is no problem with the second value as well. And we have the same situation by considering the third value for a singularity. A complex value is obtained as well. So, there are no singularities. Good. Now we must still consider the GOO component. First, there's a problem that we had 2 different versions for the function a, an analytical and a numerical one. I will explain more about this problem later. Here, I only want to say that the numerical solution is a more usable one, because the analytical one would have a singularity at about half of the radius. And this would be nonsense. So we use the numerical a function. If we look for singularities, then we would obtain the same cubic equation like we had before. We would obtain the same values for singularities. So the a function makes no problems as well. Good.
Now we can ask for a threshold value for the mass density ρ, which would move the singularity into the considered body. We take the equation for r1 and set it equal to r, the radius. I again don't show the calculation, but the condition 59 is obtained. If we suppose a neutron star with a radius of 10 kilometers, then the critical value for the density would be 8.6 times 10 exponent 17 kilogram per cubic meter. Higher values are not possible, else the singularity would move into the star. The higher the density is, the smaller the radius must be. R1 can be reinterpreted as a maximum value for the radius if the density is given. If we suppose a mean density ρ of 5 times 10 exponent 17 kilogram per cubic meter, the radius of the neutron star cannot become larger than 25.4 kilometers. If we verify that with data of known neutron stars, we find that they obey the condition 59, as far as the data are known, especially the radius. We consider a diagram where the maximal radii are drawn for the given mass densities. On both axes there is a logarithmic scale. Neutron stars, as well as white dwarfs, don't cause any problems. Their parameters lie inside the given boundaries.
Now we compare the Huppmann metric with the Schwarzschild metric. A compact and a non-compact model are considered, Sun and neutron star. Here in 60 we have the inner Schwarzschild solution. We consider the components of the metric in the order they were derived. We begin with the C function or G22 component. The RTG or Huppmann function lies slightly above the Schwarzschild one. The exponential part of the Huppmann function takes values between 1 divided by e squared and 1, the 62. Both functions show the same behavior. If we compare the boundary values, then in a non-compact model they are nearly identical because alpha is very small. In a compact model, alpha has a higher value, so that the Huppmann function yields higher values than the Schwarzschild one. Now we consider the B function, the R11 component. If we look at the Schwarzschild function in a non-compact model, Sun, here we have the function with a value 1. L is big compared to R here in 60, and so a small value is only subtracted from 1, and so we have here practically constant. Okay, the Huppmann function is continuously increasing from a smaller value, and at the border, at the radius here, the Huppmann function reaches the Schwarzschild function. If we consider a compact model, neutron star, then we see now the Schwarzschild function is also continuously increasing. And the Huppmann function has got the same behavior like before, but at the border, the Huppmann function does not reach the Schwarzschild function now. Okay. Now, if we consider the A function, GOO component, then we see here the analytical Huppmann function here has got a singularity here, so it is unusable. So the Schwarzschild function, that is nearly a constant function here, and the numerical Huppmann function lies below the Schwarzschild function. Here at the border they have nearly the same value. If we consider a non-compact model. If we consider a compact model, then the Schwarzschild function is slightly increasing, and the Huppmann function, the numerical Huppmann function, again lies slightly below the Schwarzschild function. Okay. Now we want to consider the G11 component again. We look at this diagram here. Here we have the Schwarzschild function S, and now in the G11 component is a singularity, Schwarzschild singularity. That singularity moves into the model if the body is compact enough. If we have the same radius and the mass density is increasing, then the singularity would move into the model. If we look at the Huppmann metric, and the Huppmann G11 function is increasing far later and not so much like the Schwarzschild function. So here the Huppmann metric would not make any problems. We look at a three-dimensional diagram. Here in the vertical line we have the G11 component value, and here we have the radius r. It runs up to 11,000 meters, 11 kilometers as a characteristic radius of a neutron star. And here in this direction we have the density, the mean density rho of the with a neutron star. And if we look at the value for the radius, and then the density is increasing, and then the Schwarzschild singularity would move into the model. So here where we see the high peaks here, this is the line where not the general theory of relativity, but the Schwarzschild metric breaks down. The Schwarzschild function, that is a pink function here with the peaks here. And so the gray function, that's the Huppmann function. We see the Huppmann function is continuous and makes no problems here. So the Huppmann function has got far better behavior than the Schwarzschild function. And we have to check the latest values of neutron stars. If we find a neutron star that lies beyond this border line here, then that would be the next disproof of the Schwarzschild metric. Next part, inconsistencies in the field equations. There was a difference in the two A functions, and we find some more inconsistencies. The second derivative of the C function is not continuous at the radius, at the edge of the model. The inner function yield a value of 4 and the outer function value of 2. Okay. By considering the B function, only the function itself is continuous, but not the first and the second derivative. Here we see the inner and outer value at the edge of the model. You have two different values. The reason is the unrealistic model of a constant mass density. At the edge, the density function falls immediately from a higher value to 0 in the outer space. The same problem do we find in the Schwarzschild metric. This problem can be solved by using a density function which decreases to 0 from the center to the boundary, but then a solution must be worked out numerically. Now we come to further considerations. If we suppose a more realistic and non-constant density function, then equation 7 isn't integrable elementarily anymore. Such a solution must be found numerically. Okay. Now we want to write the Huppmann metric in isotropic coordinates. So we have to bring the line element 67 into the form 68, where we have only one function for the three space coordinates. These are treated in the same way. Disadvantageously, we obtain an elliptical integral, 71, that cannot be calculated analytically. It must be solved numerically. Good. If we try to incorporate a spherically symmetric electrical charge into the model, the field equations become too complicated, so that an analytical solution cannot be derived. We had to add the electromagnetic field tensor, 72, to the energy momentum tensor that was used until now. That would lead to 76 for the OO component. So here the functions a and b appear on the right side of the equation together with the r exponent 4 term. This means the equation cannot be integrated analytically. If we want to consider the Huppmann metric by assuming a non-zero rest mass of gravitons, we find the same problem. Equation 77 would be obtained for the OO component. Here, some additional terms with the functions a, b, c, and r squared would appear. Okay. A time-dependent metric would be too complicated as well. In 10, I'll show you the literature later, we find the time-dependent equations for the vacuum. They cannot be integrated analytically, even for vacuum. Then the Fock solution is not the most general vacuum solution. Then again, we would obtain two complicated field equations. It would make no sense trying to do work with the general outer solution. To obtain the Fock metric, we had to set in 81 C1 equal 1 and C2 equal 0. Okay. Now we come to the chapter about black holes. H. Huppmann has explained that quite good, so I will read his text. It is often mentioned that there are no black holes in RTG, the relativistic theory of gravitation. This statement calls for an explanation. First of all, the theory of the development of stars requires the existence of a still more compact body than a neutron star or quark star. For, if the quantum mechanical pressure of the particles, which results from the Pauli exclusion principle, is not sufficient to compensate the contracting gravitational force, then another gravitational collapse into a more compact structure will take place. Mathematically, GTR would yield a collapse into a singularity. The singularity in the outer Schwarzschild metric represents a so-called event horizon. However, it was shown within RTG that the gravitational collapse does not end in a singularity like it is known from GTR. Yes, see literature number 13. I will show later the list of literature. Furthermore, there is no singularity which leads to an appearance of an event horizon. Singularities are hardly acceptable physically. So, in several articles, a statement from J.A. Wheeler is cited. He considered the collapse into a singularity as one of the greatest crises of all times in physics. Possibly, the new metric, which is derived here, allows a new treatment of black holes. Singularities are unphysical. It can be assumed that a black hole also possesses a certain radius and a certain density. Nothing is known about the inner structure of a black hole. The mathematical transition to a black hole is represented by the discriminant, 43, that turns from a negative into positive value. That is the discriminant of the cubic equation I had recognized. Okay. This means that the cubic equation, 42, has got only one real solution. So instead of 3 possible singularities, we have only one possible singularity here. And the radius r for the singularity is represented here by equation 82. Now, a lightweight black hole with a mass of 3 times the sun mass, that means 6 times 10 exponent 30 kilogram, is considered. The discriminant would become positive at a value of about r equals 16.88 kilometers. The radius is certainly much smaller than 10 kilometers. 10 kilometers, that is the radius for neutron stars. This means now alpha is much bigger than the radius. Until now, we had always said that alpha is smaller than r. Here we have another situation. So for the coefficients, 42, the following values are obtained. We have here in 82 p, q, d. D is a discriminant. So, and we would get the values 1, p is much smaller than 1, and q is about -1, and d is about 1/4. So that would lead to the result, this yields the interesting result that Rs is equal 1 meter. And the higher the mass would be, the closer the result would be to 1 meter. This result is practically independent of the mass. For every black hole, a singularity is found at 1 meter. Since there may not be a singularity within the model, the assumption must be made that the radius of a black hole must be smaller than 1 meter. But this result causes another problem. A singularity would be found in the outer Fock metric, the G11 component, 38, which must be used for vacuum. It is exactly the value alpha. Here, for a lightweight black hole, the value is alpha about 4.4 kilometers. Disadvantageously, a new event horizon would be yielded by theory. But at this point, it must be recognized again that all the conditions are derived in this work have to be modified in using a non-constant density functions. Models with a variable density possibly do not contain a singularity. Furthermore, it is not known how the other interactions have to be taken into calculation. The big question is, what is black hole matter made of? In QCD, it is not possible, until now, to calculate quark matter reasonably under such extreme conditions. Furthermore, usually a star has got a certain angular momentum, so an axisymmetric metric is needed. In gravitational theory, there does not exist a useful one until now. Then we still have an outlook. Huppmann writes, The next step must be to find a general numerical solution for models with non-constant density functions. With such a solution, the inconsistencies at the edge of the model vanish, and furthermore the singularity within black hole models possibly vanishes too. And of course, a useful axisymmetric solution is needed urgently that could lead to a better understanding of the structure and the development of stars. H. Huppmann has got many themes for some diploma thesis or doctor thesis, but he never would get a chair in Germany. Only nepotism and protection. You must come out of a rich family, then you get the job. It hasn't anything to do with your abilities as a scientist, your abilities in physics and mathematics. In Germany, only money counts. So H. Huppmann is thinking where he could emigrate. His hope is that there is a modern country who needs a good scientist. Germany does not need one. Now, this is the used literature. Let me tell something about it. We find here some papers from A. Loganov, Anatoly Alexeyevich Loganov. He is the father of the relativistic theory of gravitation. H. Huppmann had a very good correspondence with Professor Loganov. That was long before the Ukraine war has started. Professor Loganov was very interested. He knew what H. Huppmann's work could be worth. H. Huppmann asked him whether he could submit his doctor thesis in Moscow. In Germany, no university is able to examine H. Huppmann's doctor thesis. Germany has fallen behind hopelessly in this field. Professor Loganov wanted to send him something, but H. Huppmann didn't receive another email. What he already feared had come true. Professor Loganov had died. And obviously, since Professor Loganov's death, Moscow has given up working in this field. The articles in RTG became less and less. H. Huppmann tried to publish his paper in theoretical and mathematical physics, and they had still his paper in the list of papers which are to publish. But then it took them half a year to send H. Huppmann the message that they don't want to print his paper. My God.
Now, this is a Huppmann metric. Now it is published under H. Huppmann's name, and so nobody can steal him the work. I say thank you for watching. See you next time. Goodbye.